Good evening. Scientists, just like artists and authors, need to share what they do or want to share what they do with the world. And so being in a place that specializes in that, the Guggenheim Museum, is personally a fantastic thrill. We as scientists don't have quite the same kind of opportunities to share, but we certainly have the same desires. I'm here now, and we're here this week for a wonderful festival going on in San Sebastian, a passion for knowledge, which gives us an opportunity to share what we do with an interested public. And it's great that it's extended this time so that at least some of us get to talk to you here in Bilbao, in this fantastic museum. I'm going to talk to you today in a kind of historical context. And the reason why I'm going to approach it that way is that it's not just an illustration of a discovery in physics, a rather fundamental one, which you'll see, but the way science is done and the way science evolves. So I'm going to I entitled it Going from Einstein to Gravitational Waves, but actually I'm going to go back to Newton. My subject today is something we have all experienced at some level, so some of you are more expert than others, but everybody knows something about gravity. So what we learned, and I think all of us share, is basically what Newton told us about gravity in the 1600s in a book called the Principia. And in that book, which is also, by the way, where he wrote down the scientific method, which is what we all use to ascertain truth in science, he developed and wrote down basically what he called the unified gravity, for the first time putting together a way to understand gravity in what seemed to be very disparate roles. For example, we all learn about the apple falls out of the tree and falls to the earth. That doesn't seem very connected to why the moon goes around the earth or the earth around the sun, but he managed to understand that it was really the same physics phenomenon that explained everything that he could see having to do with gravity. And as kids, we all learned that. If you learned a little bit more, you probably saw this formula. And this formula is the formula for universal gravity. It says that if I have two objects, the gravitational force will be inversely proportional to the square of how far apart the two objects are, and proportional to the mass of one times the mass of the other, with some unknown constant in front, which again, reflecting on the science, he couldn't determine, and it took another 100 years before it was determined, when a special technique was developed called a torsion balance. So this was the formula. He developed it in much more detail than I'm going to talk about today. He did the calculus to show that you can take the center of gravity of each of these objects, and he put it forward in this historic book. It basically is arguably the most successful theory of physics ever. It lasted over 200 years in the form that I'm saying, this formula. And it's not wrong. It basically was changed and evolved by necessity by a new theory, which I'll describe briefly to you, introduced by Albert Einstein in the beginning of the 20th century. So from 1680 to 2015, this theory managed to describe everything that was measured physically except for one small flaw. And that flaw was the orbit of Mercury around the sun. So I'll remind you that Mercury is our planet closest to the sun, and it has a very elliptical orbit. Each time it goes around the sun, it gets pulled by the presence of all the planets, the moons on the planets, and so forth, and it comes back to a slightly different position. It looks like kind of what we call a daisy pattern, which you can see up here. And as physicists, we can calculate, using Newton's theory, how much it should move each time it goes around. And the answer turned out to be slightly wrong, about 10% wrong. So I give it down at the bottom in some complicated units, but it's basically the description of how far it'll move. This was the only place in more than 2 or 3 centuries that the theory of Newton had any discrepancy at all. It was believed that in the 1800s, mid-1800s, by a French physicist, that the easiest explanation for this is that there's some sort of matter between Mercury and the sun. And in fact, he proposed that. It was searched for. There were false discoveries, people who thought they saw something, but then it was disproven. And by the time Einstein came along, it was still a puzzle. But it's a 10% error in one thing that could mean they haven't yet found what's between Mercury and the sun. And in fact, it also is true that one of the earliest big missions by NASA was, which is long after Einstein, was to look and see if there was something between the sun and Mercury. In fact, they didn't find anything. And so Einstein introduced a new theory of gravity. The new theory of gravity means it's formulated quite differently. It obeys all the things that we learned that Newton said, and it does something more. And his theory of gravity, if we write it down, it's a little more complicated. I just use one formula, which is harder to understand, and I'm not going to explain it in detail, but just to show you, it's the main formula for his theory of gravity, which is called general relativity. And general relativity, everybody knows E equals mc squared. This he introduced in 1905 in the theory of special relativity, which is that when anything goes very fast, near the speed of light, that their rules change, basically, and that's the theory of special relativity. He then spent 10 more years, between 1905 and 1915, adding not just velocities going near the speed of light, but accelerations. It turns out that accelerations mean gravity. I won't explain why, but they mean gravity. So he did this by something that are the words you find in all the popular press. He unified space and time so that it's one word. It turns out that Bill Gates at Microsoft still doesn't understand that because he puts a little wavy line on it, under it, if I use Microsoft Word to write it out. But the unification is what is done. You solve the problems geometrically of gravity in a 4-dimensional scheme. I'm not going to go through that for you, but the results are very interesting. First, it does what any new theory or improvement on a theory should do. It gave the right answer for Mercury around the sun. That certainly doesn't make it right. And when we talk about a new theory, when somebody comes along, solving an old puzzle is just the first requirement. There may be many, many clever ways to solve a problem that's around that may or may not be right. To make a theory something that we take seriously, it should predict something new that we can measure and wouldn't have been true otherwise. And that was true of Einstein's theory. Secondly, and maybe more importantly than what new it produced, which will be kind of the rest of the lecture, it explained some features that were not explained in Newton's theory, one of which he understood was a problem himself. The first one is that in school, when we were little kids, most of us, our teacher told us if we jumped up, the earth pulled us down. And we believed them, believed the teacher. But I don't know how many of you, but not me, didn't ask the teacher why it pulled you down, because Newton didn't explain that. He gave us the formula, but he didn't tell us why it pulled us down. And in fact, through the 1800s, people tried to explain it, usually with schemes of electricity, because that's the force we knew, and electromagnetics, and it had nothing to do with the answer. Einstein explained it because when he introduced this combination of space and time together, it warps space-time. Everybody's heard those words. They're in movies and so forth. And it basically can be seen in this picture here. If I have a grid, this is a grid like a coordinate grid, but think of it as like a trampoline. If I put a mass on the trampoline, it distorts the trampoline. And then if I want to put a mass out here, it'll be attracted. It'll fall down the hole. And that's basically the apple falling toward the tree. Also, the moon going around the Earth is the same thing. If it's going around this way, it'll stay at the same level instead of climbing up the hill or going down the hill. And that basically explained already something pretty important that Newton didn't, even if you forgot to ask your teacher why the Earth pulled you down. The second is even more important because we need it so much to describe the universe and the physics which has come beyond after Newton in describing astronomy. And that is, it has a concept, and I'll use the words. In Newton's theory, when you have these two masses, the force is felt immediately. There's no time delay, meaning you have instantaneous action at a distance. Wherever it happens, the apple falls, you know it immediately. That's not physically right, and Newton knew that, but he didn't know what to do with it. So he basically alluded to the fact that there's a problem of instantaneous action at a distance. You can tell that it's true just in the little example I give here, because the sun, if the sun were to disappear right now, we wouldn't know it for 8 minutes because that's how long it takes the light or the heat to get from the sun to us. Similarly, any effect of gravity or anything else has to take some finite amount of time. In Einstein's theory, he realized that there's really one time, and that time has to do with these coordinates and so forth, and we call it the speed of light, but it's the speed of information, the finite speed of information to travel. Of course, the speed of light is very high, so when the apple falls, it doesn't really matter to us, but if we start doing astronomy, then it does matter. We look at objects much further away than the sun. So those are the two practical are conceptual problems that are fixed by Einstein's theory. But then he made a new prediction. And the new prediction is that since you have this distortion of space around an object, if any other object comes near it, it'll get moved or it won't follow the path of a straight line. And it really doesn't matter whether that object has mass itself or that object is light. So in his idea, light itself, if it comes near a massive object, will bend. And that was an important and dramatic concept. Not only that, he calculated exactly how much it would bend if light grazed the sun. That may seem like something, why that? Because he envisioned a way to test that. That is, look at the sun at exactly the time of an eclipse of the sun, when it's dark, and watch the stars behind it as they move toward the sun, and the light that grazes the sun will be bent, just like in the picture here. And that basically was the experiment done by Eddington in 1919. Einstein proposes in 1915, and that made a huge effect, and people believed for the first time, even if they couldn't understand the theory very well, Einstein's theory. This is the headlines from the New York Times at that time, which it kind of shows the shock of all the attempt to explain light bending, which seemed like a crazy concept. Einstein actually went on to become famous worldwide because of the publicity of this. For physicists, he was famous long before this, in 1905, when he solved 3 or 4 of the most important problems in physics within a matter of a few months. So for us, in 2005, we celebrated the centennial of Einstein. But for the world, it was really general relativity and in fact, the bending of light that made him a household name. Okay. Like all things, when we learn about them, we learn useful ways to use them. So it turns out that astronomy uses the fact that light bends in very clever ways now by finding the fact that you can study something about the emission from some source if you look at it on the Earth as the observer in this picture as it bends around some object that could be black in between. And so that's called gravitational lensing, and you occasionally read somebody discovered something using that technique in astronomy. It's a common technique now used in astronomy. You can look at an object and see the bending of light behind it fairly readily now, and I show it there, and especially if you look at probably the most famous example, which can be seen on the right day in the right climate with your naked eyes, and that's what's called the Einstein cross. So that's all an advance. But I'm not going to tell you very much more after this slide of anything that's useful, because I don't know. But it turns out this very abstract theory of Einstein's general relativity is used by probably almost everyone in this room every day, and that is GPS, the positioning system that we use to tell where we are, whether we're in a car driving down a road. And it was realized as they were building the GPS system, first being built for military purposes, that you couldn't just take how long it took the signal to come from the different satellites. There's 24 satellites spread around the world, and you compare the times it takes for the signal to come back and forth between several of them to tell you where you are. But the satellites are going very fast. They're up high, and they're going about 14,000 kilometers an hour. That's fast enough, so they're what we call relativistic, and so you have to make a relativistic correction. When you study physics and you study relativity, there's a saying that goes with it, and that is moving clocks tick more slowly. You've probably seen that in science fiction or whatever, that if you're on the moving object, maybe you age more slowly and so forth. So basically that correction, it turns out, for how fast the satellites are going is about 7 microseconds a day. And that's made in the satellites. So they make that correction, and you never know it, so it's made, and you know where you are. But it turns out that general relativity, my subject for today, is also affects the clocks, because the gravity up where the satellites are is only about 1/4 of what it is here on the Earth where we are. And the correction is actually much larger than for special relativity. It's 45 microseconds a day and the other direction. So the total correction is 38 microseconds a day. That doesn't sound like a big correction. But if I put the numbers in, I'm not going to go through them with you, and ask how accurately I can tell where I am as I go down the road. If I didn't make that correction, how long would I stay on the road? So if I take and assume the road is pretty wide, 10 meters wide, it's about 2 minutes. So without this correction for general relativity, you might not have gotten here tonight. So let's go on to my subject. Any new theory like this, in addition to predicting something we already knew, if it's really profound, predicts something we didn't expect at all. And in this case, Einstein in 1916, not in the original formulation, which was 1915, realized that maybe gravity had another new effect. And that's what we call gravitational waves, what I'll spend the rest of the lecture on. What he did is write a little paper. It's less than 10 pages long. It's not very mathematical. And he didn't derive out of the details of general relativity that there were gravitational waves, which I'll define for you in a few minutes better. But rather, he noticed that in the equations, if he set them up a certain way mathematically, they looked, although the letters were different, they looked a lot like the equations of electricity and magnetism. But we know there's electricity, there's magnetism, but there's also electromagnetic waves, radio waves, light waves, microwaves, and so forth. So being Einstein, he made the leap. Since the equations looked alike, he predicted there must also be gravitational waves, waves like the light waves we talk about, but having to do not with electricity and magnetism, but to do with gravity. And he wrote this paper. The rest of the paper, other than this great insight, is poorly written. It's got mistakes in it, but it's the classic paper that predicted gravitational waves. 2 years later, in 1918, he wrote a second paper. In that paper, he fixed his errors. Being Einstein, he never admitted there were any errors. He just went on. But it's done correctly in the second paper. And in the second paper, he did something really important, and that is he told us what the source would be to make gravitational waves. How do you make a wave that's gravitational like you do electromagnetic? So let me remind you what was done electromagnetically. a physicist named Hertz in the 1880s proved that there are electromagnetic waves. And he did this by basically making a source, which is two charges, oscillating them like this, and then going into the next room and detecting that those two charges, when you oscillated them, made waves which were electromagnetic. He detected them, and then he moved toward the source and away from the source and saw that they were wave-like. And so that was the proof of electromagnetic waves. That then we'd like to try to do also for gravitational waves. And I'll talk for a second about that. The way that you can see then that kind of source making a signal, to jump ahead a little bit, is if I have two objects going instead of this way, like Hertz saw, but going around each other, they will make gravitational waves by what Einstein saw in 1918. And that's the picture of the black holes that I'm going to show you colliding in a few minutes. So to stay with my historical approach first, is Einstein himself developed some doubts whether there were gravitational waves in the 1930s, 20 years after his initial prediction, when he tried again to see if he could derive them from the heart of the theory instead of just the equations look similar. And in doing that, he found infinities, what we call divergences in the equations, which made him doubt that he had the right answer. And so he turned in a paper to be published that said that. And that paper basically was first, 20 years after he predicted gravitational waves, he wrote a paper that said, are there gravitational waves? That paper, basically, by the time it was refereed and so forth, it's a long story, but I can't go through it tonight. It finally was published in not questioning whether there were gravitational waves, but also not proving that there were gravitational waves. So the doubt whether there were gravitational waves or not went on into the 1950s. And in the 1950s, there was finally a meeting of the theorists that studied general relativity in a place, Chapel Hill, North Carolina, in 1957. And at that meeting, for the first time, a physicist named Pirani, a British physicist, derived from the heart of the theory gravitational waves formally. And my colleague at Caltech, Richard Feynman, was at the meeting, and he said, physically, if there's gravitational waves and they're real, they have to be able to transfer energy. So you can talk about waves going through, but if they don't do anything, what does it matter? They have to be able to transfer energy. And in physics, before we can do an experiment, we often do one in our heads. We call it a Gedanken experiment. And he presented a Gedanken experiment, which is shown here. And the idea is that if you have a bar and you have a couple of rings around the bar, almost a picture we saw in the last talk, and a gravitational wave were to go through, it distorts space and time. It takes the bar in the middle and expands and compresses it a little bit. That then presses on these rings. They'll move, but what it's doing is causing some friction, which makes the two rings move. Friction is heat. That's energy. And so that's the conceptual idea that you can transfer energy. So that made the problem then experimental. If there are gravitational waves, then we have to see that they actually exist in nature. And that turned out to be a quite hard problem that was started in the 1960s. So what's hard about it? First, the amplitude. We heard in the last talk how small a nanometer is, 10 to the minus 9. Everything I'm going to talk about from now on is 10 to the minus 21, not 10 to the minus 9. And so we have to see an effect that's one part in 10 to the minus 21. That's a really incredibly small number. To put it in perspective, it's 1/1000th the size of a proton, is the size that we have to be able to see a change of effect that comes from gravitational waves. What's the reason for that? I'm not going to explain it to you. It's not because gravitational waves are some obscure small thing. It's that their effect on us is very small because going back to my original words, we have a distortion of space and time. We usually think of space as empty. It's not empty. Otherwise, what does it mean to distort space and distort time? So it can be distorted. But if you think of it like a material, it's very stiff. And so it's like having a material that doesn't bend very much. So we can't really distort it very much with gravitational waves. So even though theoretically, or I can write down the equations, it looks like anything else, it turns out that the universe that we happen to live in, it has space that's very stiff. And so we don't really see very much of an effect, but we have to try to measure it anyway. So what does it do? If I had a ring like this, and these masses were absolutely free to move, they're not sitting frictionally on something, and a gravitational wave comes through, it's going to make an effect of 1 part in 10 to the 21. What does it do? It distorts it so that it's elliptical. So here I show the distortion that it's elliptical. If I started with a circle that's 1 meter, it would be 10 to the minus 21 meters. As I said, that's a pretty small number. So the first thing we do is decide to make an apparatus that's very large as we can get away with, to try to make the size of this circle as big as we can, which makes the effect smaller. So we make the device kilometers instead of meters, and that's the reason it's so big. Okay, before I talk about that, let me just say that if I'm an experimental physicist and I learn in school how you approach experimental physics, or any science, I think chemistry, biology, is you want to control all the variables. If you want to be sure about what you do, you control all the variables. So what you want to do is what Hertz did. He made the source, he made the receiver, he moved things. There was no unknowns in the problem. So what we would like to do is make a laboratory experiment where you did the same thing. We created a source for gravitational waves, we know what it is, and then see the response. But the trouble is, I've made a source here, which would be a spinning barbell. And if I do that, and I make it unreasonably large, make the two masses on the ends 1,000 kilograms, make it a meter long, and spin it 1,000 times a second, this is all kind of exaggerated, and go 300 meters away and try to measure it, the size of the effect is not 1 part in 10 to the minus 21, it's 1 part in 10 to the minus 35. So our ability to make our own source of gravitational waves is much, much smaller than what I'm going to talk about for the rest of the talk. So even though we don't like it, we're forced to try to find something in nature, even if we don't understand it very well, to make the gravitational waves for us. We happen to have been very lucky because what we found for a source ends up being so interesting itself that we're doing all kinds of science with that source. But that isn't by my design or our design, but by the fact that we just happen to, the source being black holes, which are an interesting problem. So what we have instead, to jump ahead, and then I'll show you how we get there, is 2 black holes that are going around each other like this. And the parameters of them I show here. They're each 30 times the mass of our sun. That's 10 million times the mass of the Earth. They're about 100 kilometers apart when I show them to you. They're going around about 100 times a second. And the distance away is 1.3 billion light years. And with that, I get this number of 10 to the minus 21. So I'm going to show you the effect kind of backwards by saying that. The technique that we use is a technique called interferometry. And we're lucky that there's a technique that can be made very, very accurate. Although for us to make it for this purpose very accurate took us 21 years. And that is what's called interferometry. You remember the little circle that I drew? It got made into an ellipse. So the best way to test that is have two sizes perpendicular to each other and check as carefully as you can that the length is the same in both directions. And let's see if my movie doesn't show. So let me go on. So instead, you can see the problem here, that if the 2 arms are the same length, then the light will go down the 2 and come back at exactly the same time, and we will have a cancellation between the 2, and our detector, which is on the bottom where it says sensor, will see nothing. But if one of the arms gets longer than the other, I show it here at a couple hertz going, then you see some light going through. That's the technique. we've made this technique incredibly accurate. And I'll characterize how accurately by two numbers. The first, a few of you probably have once in your life been in a laboratory and seen an interferometer somewhere. And that interferometer, usually you see fringes on the light that has to do with the light of the laser beam. And you can measure something to some fraction of that wavelength, or the wavelength of the light, maybe a tenth or 100th or something. We have to do it to 1 part in 10 to the 12th in order to get this 10 to the minus 21. And that was a huge challenge, and it took us years to do that. I won't talk about that in any detail because it's kind of a detailed, I would call it, engineering problem. The second is that we are trying to measure gravitational waves right here on the Earth. And the Earth might seem pretty stable to you, but it isn't. It's moving around all the time, especially compared to 10 to the minus 18 meters or whatever we're trying to measure. So we have to actually take this device, even though we're here on Earth, and isolate it as well as we can from the Earth itself. And we do that, and I'll concentrate on how we do that to show you what is necessary to make this measurement. LIGO consists of two devices. They were funded in 1994. We succeeded in 2015, 21 years later. They were funded in 1994. They're 3,000 kilometers away, one in the state of Washington and one in the state of Louisiana. It may seem like a funny place for the two. The two institutions that proposed this were Caltech in California, my institution, and MIT in Boston, who were collaborating on this. We proposed it and, of course, had a site not so far from us in Southern California, in southern Maine near MIT. They funded us, but they chose different sites. As you can see, they rotated it by 45 degrees. And but we ended up with two friendly senators who helped us through the years, so it was okay. These are the two sites, and you can see they're very different. Louisiana is very swampy. It's in the middle of a commercial pine forest where they cut down the trees to make paper. And on the side of that's water. So the water level is maybe a millimeter below the ground in Louisiana. And so we have to build the apparatus up high. And so this is up on a berm up high, like a highway's built up high enough so it doesn't flood. In order to get the dirt to build it up here, we made a borrow pit along here, and it immediately filled with fish and crawfish and regular fish and even alligators. So. And then the local hunters came along, and we had more of a crisis. The two sites are very different physically, but the technique is exactly the same. And if we isolate ourselves from the shaking of the Earth the same, they behave the same. And I think in one of the plots that I'll show you, you'll see that they behave exactly the same. This is what it looks like. I'm just showing you this to show you there's real apparatus. It's in high vacuum, which it has to be in. And all these little shiny ports are ways that we can get in and out and change the apparatus. We needed that from the very beginning in order to have enough flexibility to keep evolving this through 21 years to make it a good enough device. It's also true usually in large-scale physics experiments that the infrastructure, this kind of stuff, is much more expensive than the high-precision instruments that you put in. And so you want to build an infrastructure that you can keep using and just put your money and talents into the detectors and techniques themselves. This is the glass that we use for reflecting the light back and forth. And this is the key to the measurement. So basically, we had to get 10 to the 12th isolation from the Earth. How do you do that? Well, we know a way to do it. And you, again, like what I said before, you use it almost every day. An automobile manages to go over a bump in the road, which is a high-frequency bump, and you don't feel it very much. It does that because it has shock absorbers. The shock absorber absorbs the energy at high frequency. It can't get rid of it. It just goes to lower energy, and you see yourself smoothly go over the bump, and you don't feel it almost. We want to do the same thing. We work at frequencies that are high frequency, and which are available to us in the Earth, and we just want to make very good shock absorbers that move the shaking of the Earth out. So we undertook to make the world's best shock absorber system. And it is just the perfect squishiness for the springs and the shock absorbers. It's 4 layers, and it's in that picture that I just showed you. And that picture here didn't quite get to where we wanted to get, even though we worked on this for more than 15 years. So we had to add another technology, and again, we just borrowed one. So the idea, not the technology. And the second one, so we got maybe 10 to the 10. I said we needed 10 to the 12 by all these shock absorbers. But there was residual shaking. So how do we get rid of that? The idea then was borrowed again from not cars this time, but maybe airplanes. Many of you have, when you go on an airplane, get bothered by the roar of the engine, so you put on these little earphones, and magically the sound of the engines kind of recedes in the background, and you can even hear the stewardess ask you whether you want coffee, tea, or whatever it is. So what's it doing? It's basically measuring the ambient sound that's coming from the engines and canceling it. So we want to do the same thing. It's not the same application, but the same idea. We want to take whatever movement there is from the Earth, sense it, and cancel it that's left over from these shock absorbers. So we buried inside of this big array active seismic sensors that could tell also the direction. We measured where it's coming from and pushed back against any motion of the Earth, and we gained another factor of 100. And with that, once we turned it on, we were able to detect gravitational waves. So now I'll show you the result. This is a picture of 2 black holes. And these 2 black holes are the ones that are drawn from the data that we have. It's not an artist's animation, but it's a picture in the universe. And this story starts 1.3 billion years ago. So what I'll show you happened 1.3 billion years ago. If we go back 1.3 billion years on the Earth, we were just evolving from single cell to multi-cell life. So that's when this happened. And it took a little while to get here, and so we had some time to get good enough to find them. They're black holes. So let me remind you what a black hole is. A black hole is a mathematical concept. I won't give you that, but it's a concept where gravity is so strong that nothing can escape. An object that's real, but nothing can escape because gravity is so strong. Now, I showed you a little bit that light bends around gravity, so even light can't escape if gravity is strong enough. So that's a black hole. Nothing can get out of a black hole. How does a black hole come about? It comes about from a star that burns up all its fuel, and then it collapses by gravitational force. And if the star is big enough, it'll make a black hole. Our sun won't. It's just too small. The amount we can calculate the amount of gravity that it'll make won't be enough. But if you have a star that's 3 or more times the mass of our sun, then when it collapses out by the gravitational pull, the gravitational field will be so strong that it makes a black hole, or can make a black hole. And that's what we call stellar black holes. So stars were the originator, and we make stellar black holes. Now, this movie's not going to show either, so we won't watch it. But this movie that I had on here, which isn't showing, shows these 2 objects coming together. But the picture itself, just to emphasize what we're seeing, is 2 black holes that are separated by about the distance between San Sebastian and Bilbao. They're about the size of these black dots here. Each of them are 10 million times the mass of our Earth, 10 million times. And they're going at about half the speed of light when we detect it. Now's when you stop believing me if you didn't earlier. But that's basically what comes out of this. So they're going around at this speed, in this distance away, when we start observing them, when they're going around fast enough that they're at our frequencies. Then they propagate to the Earth. My movies aren't working, so they propagate toward the Earth. And when they get to the Earth, which is 1.3 billion years after it happened, Then they come up through, this one came up through the southern hemisphere on September 14th, 2015. We know the position to this accuracy, not very good, we're better at it now, by when it was detected in Louisiana and when it was detected in Hanford, about 7 milliseconds apart. So 20 milliseconds after it came through the bottom of the Earth, it came and made this trace, and this is straight data. It's not gone through a lot of computer analysis like none, and we get this figure here. On the vertical scale is the scale of 10 to the minus 21, what I told you, and the peak of these is about that big. And the horizontal scale is about 0.2 of 1 second. So what we saw is what we call a chirp signal. It's a signal that's getting bigger and narrower or higher frequency. It goes whoop as we go through it. And that's exactly what we expect from Einstein's equations of two black holes like I showed you coming together. 7 milliseconds later, we saw this in Hanford, Washington. It looks, within the accuracy of our measurements, very much like the first one. So that's why just seeing this one event, this looks so good. I've now drawn a line through it, but you can probably not see the difference except maybe a little brighter. That line is the line I get by taking Einstein's equations, taking those two black holes that I showed you, and calculating what it would give. And you can see it looks exactly like the data so well you can't see the line. And so that's what convinced us so quickly that once we did the experimental checks, that what we saw was two black holes colliding and giving gravitational waves. Since that time, we've seen and reported about 10 examples, different masses, different distances away, and so forth. And this is giving us now, like always for the next step in science, some information about what the origin was of these black holes, how early in time were they created, what's the mechanism to make them pairs, and so forth and so on. And that's the science we're doing now. In the lower right-hand corner, there's another one that looks very different. And that is a picture of the first time we've seen another source. And it's not black holes. It stays in our apparatus for tens of seconds. Similar kind of pattern, but much, much higher frequency and going for much longer. And we identified that again using Einstein's equations as two what are called neutron stars colliding. Neutron stars are one of the remainders of the collapse of a star if it isn't heavy enough to make a black hole. It has a nice feature that it's just very compact nuclear material, which means it'll have nuclear reactions. And so when it collides together, there's other things besides gravitational waves that you can try to detect. And we got lucky because we got lucky because at the same time as we saw that, the satellite looking at gamma rays from what are called gamma ray bursts saw the same object 2 seconds later, and we basically knew from that we saw these neutron stars, and we've been able to study various effects with that. Despite the fact that what I've shown you may seem like we're at the end of the road because it's so accurate, we're still limited by us and not nature, meaning that we can keep making a better apparatus to measure gravitational waves better. It's not nature that's stopping us, it's our ability to make the right instruments, and we know how to make them better. This is an example of a study here in Europe, in which there's Spanish collaborators on it, of how you would make an apparatus that would be at least 10 times more sensitive than what we're using in LIGO. You put it deep underground, you make it a triangle instead of L-shaped, you cool it to low temperatures so it doesn't make noise, and so forth and so on. With that, we can envision that we can actually keep improving the sensitivities, which is what it's showing on the left, to such a point that we could see events like we already saw, these black hole events, all the way out to the edge of the universe. We only saw 1/10 of the way out so far. If we can see out to the edge of the universe, it means we see out to the beginning of time. So this, for the first time, will give us direct information about the evolution of the universe from the time of the Big Bang at the very earliest times. So the future is, in my mind, almost unlimited. We can't do it all now, we can't do that now, but what can be done in the coming years. Not only that, that's here on the Earth. But we can study gravitational waves by going in space, and there's an experiment to do that. And we can study it by studying various impacts on, for example, cosmic microwave background. And this gives us different frequency gravitational waves. The frequencies we looked at were the audio band. That is the band that's available to us on the Earth's surface, and our ears have learned that that's where the Earth is quiet enough. But like astronomy, where we do astronomy looking at X-rays, microwaves, light waves, and so forth and so on, which has been the big breakthrough of the last 50 or 75 years in astronomy, looking at the same phenomenon in different ways. The same thing will happen for gravitational waves. We can look for it in all these different wavelengths. We can look deeper in the universe. And so the future, as I see it, is just barely beginning. It's a little bit like, and it's a little presumptuous, but I'll say it, it's a little bit like the birth of astronomy. In 1687, Galileo, for the first time, took lenses that were made for glasses, and he made them into a telescope, and other people made telescopes at the same time, but he made it into a telescope and did astronomy, first astronomy ever done without the naked eye, and that was to look at Jupiter with a telescope. And when he looked at Jupiter, he discovered there were 4 moons of Jupiter. There's more now that we know, but there's 4 major moons of Jupiter. And that was the beginning of astronomy. And we know now how much astronomy's evolved in 400 years. And in some sense, we have another way now, a very different way of looking at the universe, and we're just at the very birth of that as a field. And I'm sure that in 400 years, what we'll learn will be worth another invitation back to the Guggenheim. Thank you.